Okay, we're here to share with you some literally up-to-date information that literally happened yesterday. So I'm excited about it. I want to draw attention to, it's about the self-anchored suspension bridge. It's one frame of the entire San Francisco-Oakland Bay Bridge. If we can go back one, Victor. What I want to do is I want to focus on SAS and the tower. I want to zoom in on the pile cap. That's at the very base. Next slide, please.
Can you back up, please? I'm sorry.
Sure, no problem.
Would you mind backing up one slide?
Again, every one of these slides, I can give them to you. I can give them to Leah, and you can walk out of here with the file, or she can email them to you. It's a PowerPoint file, so it's pretty easy for you guys to use as you wish. Okay, so the focus is right. Okay, yeah. One more? Okay, cool. Okay, good. So if you go back in time, and I can take you back to the tower footing, that's the E2T1 contract. American Bridge Floor has built the SAS superstructure for us. KFM, a joint venture of Kiewit, FCI, and Manson built the marine foundations under the SAS. This is what the T1 foundation looked like before the tower went on it. You can see some 424 3 and 4 inch diameter high strength rods that are sticking up. Okay, and that's what we're going to be talking about a little bit today, but you see a lot of other reinforcing steel as well as dowels. Next slide, please. Okay, I want to highlight that this pile cap, it's a very unusual pile cap. It's a lot, it's a lot like the Skyway, these very large bridges like Benicia, like Carquinez, like the Bay Bridge. The foundations are unusual. They're super strong, super big. This is a shot of when the T1 pile cap came in. Notice it's structural steel, right? It's major structural steel. Normally pile caps up and down the state of California, they're typically reinforced concrete. This is major structural steel. This is 50 KSI steel. Super strong stuff. There are 13 piles. You see the 4 areas where the 4 tower legs come down. Everybody keeps talking about a self-anchored, single tower self-anchored suspension bridge. It may have a single pier, T1, but it's really, really important. We have 4 steel towers going up at T1. So it's a lot more redundant and complex than people think. So, and that's a very good thing, that redundancy. Next slide. Okay, some people have been concerned about, oh my gosh, we've got 1 or 2 rods that might have a question. I want to make sure you understand that at the base of this tower, okay, we don't just have these anchor rods. The anchor rods protect and help resist rotation, right? Basically tipping. To keep the base of the tower from scooting, and we call that shear action, displacement, translation, we've got 152 6-inch diameter steel dowels. So these are these dowels, and I want to make sure that everybody understands this, that's one of the reasons I'm very confident the base of this tower is not going to be scooting anywhere. Again, these dowels carry the shear. That keeps it from scooting, right? Next slide. And those are great shape. Okay, if you go back in construction, this is what they look like. When E2T1, when T1 was built, the foundation, we had something that some people call booties. These little black shrink wrap elements. They were there, placed on there to keep water from going down. Okay, that was the idea. Protect these steel pipes, these cylinders, where the rods go down in to keep water from coming down in there. I'll be straight up with you. As engineers, we've investigated this. These didn't work. They didn't work as well as we wanted. Okay, there is some water down in there. We're aware of it, and that's what construction does. Construction did a really good job. They found the water, and I'm not afraid of bad news. I want to know about things like that so we can address it. That's really important. We're not the kind of people who bury our head in the sands. Okay, so this issue is potentially part of the problem. Next slide. Okay, I want to make sure we're straight up, we're 100% transparent. Construction found water at the site. Here's a photograph, and we've shared it with the TBPOC, Toll Bridge Program Oversight Committee. Right? So we're aware of this, and that's what we're addressing. Next slide, please. Okay, construction, some people have said Caltrans stumbled across the water. Caltrans did not stumble across it. Bill Casey right here, our resident engineer on the self-anchored suspension bridge, he and his crew and his construction engineers found exactly this out on the site. they found some water as they were doing their final walkthrough. Just like when you buy a car, you walk around, you go, kick the tires, how does the paint look? Do the doors work? Does everything work? You walk through a house or a condominium, does the dishwasher work? Is the paint good, etc.? Well, they were doing that exact same thing, and they found some water. And they sent it off to METS, our materials testing people, and they said, where's this water coming from? Tell me about the chemical content of this. Then they also started looking a little further, and that comes from 20, 30 years of experience from people like our resident engineer, as well as folks like Bob Rignano there in the back. Okay? And then what they did is they also saw some caulk lifting up. Again, this comes from experience. They found this. And then they started to explore, let's peel this back, let's take a look. And when they peeled it back, they found some water underneath there. Okay, they didn't stumble across it. That comes from experience. That comes from knowing what to look for, right? So this is what they found. So this is where this whole thing started. Next slide, please. A little further, we found several conditions. We found some conditions where grout was done as it should have been per contract. We found some areas where there was no grout whatsoever. We found intermittent grout. We found some areas where there was only grout on the top, like 6 inches or foot, and there was nothing down below, and we found water there. Next slide, please. Okay, now, this pile cap, as I showed you before, you saw it as if you were a bird flying above it. You saw it from an aerial shot. Okay, let me take you inside the concrete. So if I can magically use, modern technology, and this is a company that we use here in Northern California called NorCal, and they've done some of the shop drawings for us in construction to help us make sure we could build it properly. So if I can magically take off all the concrete, and I can show you the reinforcing steel, the high-strength rods, and the piles, this is what it would look like. And we're using color for in construction and design. We use different colors to help us differentiate as we talk through challenges or problems or things we might anticipate. So this shows you all the reinforcing steel, all the structural steel, and all those 424 high-strength rods and those 152 dowels, as well as layers and layers and layers of reinforcing steel. So this is what T1 looks like underneath the concrete. So if I magically take the concrete off, again, these slides are completely available to you through the PIO office. Next slide. Okay, now, if I can use technology again to cut a piece of it out, cut out a 90-degree chunk, quarter of it, So imagine a pie and you cut out a quarter of the pie. You see elements of the piles that reach down, the 13 piles that go down deep. Okay, you also see the structural steel pile cap. Structural steel, you see the reinforcing steel, you see the rods, the dowels, but you also see what those high-strength rods, and that's what one of these is, reaching down deep into the pile cap. This pile cap, it's about the size of a basketball court, okay? So you could land a helicopter on it. This is pretty big. This is about a little more than 5 meters deep, 3 feet in a meter, so on the order of 15, 20 feet, something like that deep, okay, to give you a sense of how deep this is. And these rods, as they connect potentially onto, in the future, they will connect onto the tower, and they do right now. They go deep into the box, deep into the structural pile cap, and they connect down onto lower plates. The blue area here, that's the lower plate, and down below that lower plate is a nut, that locks this down, And that's what reacts against this tension. All of this area inside here was filled in with flowable concrete, a very specially designed concrete. So it's all filled up with concrete. Next slide, please. Okay. I want to let you know, I want to share with you a map and the location. This is a view if you cut a horizontal cut and you look downward. These round circles are the big piles that go down into the rock underneath the bay. All these black dots, those are all the different rods, anchor rods, these, and they're anywhere from 3 inches to 4 inches in diameter, high-strength steel, minimum specified strength, 140 KSI, standard steel is 50 KSI steel. Now this is the one, this is the location, this is the north arrow. Engineers, we always like to put a north arrow on it, so you have a sense of, this is Oakland, this is San Francisco. This is the location of that one rod that we asked the TBPOC if we couldn't please remove because we wanted to investigate it. Next slide. Okay, I do want to let you know, because we found water, construction and METS have been working very diligently to sample the water, and we want to understand what the chemical composition of that water is. Because we're looking for 150 years, we want to understand what that water is, we want to understand the chemical composition, what's in it. Like for example, is there bromide, is there fluoride, are there chlorides? What are we up against? And then we can do testing and investigate it, accounting for the environment that it's actually in. So that's what we're doing. This is a shot of our METS people inside the tower box, and they're doing the appropriate water sampling. There's a very, very, very rigorous protocol. We brought in specialists in chemistry just to make sure we do this properly. There are elements here, and if you want to, you can talk to our specialists or representatives of the company and supervisors of the people that are supervising that kind of chemical sampling. And then we'll incorporate the chemistry that we find from that testing. We'll incorporate it into our evaluation for the next 150 years. Okay, so this is an image right inside the tower. Next slide. Okay, I also want to let you know, I remember some of you were at the TBPOC meeting 2 meetings ago, so about a month and a half ago. And Steve Heminger, the chair of the TBPOC, said, Brian, can you do a test to verify that, verify that no rods are broken, or can you check if the rods are broken or not? And I said, I think we can do that relatively easily. And what we did is we turned to our METS people, and we used technology, and some of that technology, METS folks here can talk about this. This is an ultrasonic a testing device, and what you do is you send down a pulse down the rod, and if you know the modulus, you know the material properties through which a pulse wave travels, and you know the time. So imagine a very sophisticated stopwatch. You send the pulse down, you know exactly when it starts, you know how fast the compression waves travels through a type of material, and then you measure, you collect when that pulse bounces off the bottom, comes back, so you know the time it takes for the wave to go down and back. You know the velocity at which a compression wave travels through a material like this. The only thing you don't know is how far it travels. So you can back calc and determine how long the rod is, right? How long of a trip it took. So you take that length, divide it by 2, and that gives you the length of the rod. So METS people use sophisticated technology to determine how long the rods are. Next slide. This is a shot. So basically they use this device. Here's the computer system, right? Here's the transducer up on top. It sends a pulse, ultrasonic pulse, down the rod and back. Pretty sophisticated technology. So here, they apply the transducer. It sends the wave down and back. Okay? And that gives us a very accurate length measurement. Next slide. Now what we found was, on those rods that we tested, okay, all of them looked, quite frankly, as pretty much as we expected. There's always variation. The variation seemed reasonable. There was an outlier. Look at this one. There was an outlier. So what we did is we came back to the TBPOC as a team and said, we'd like to do even a more sophisticated kind of test, okay, on this one rod. Okay, next slide. And it was a load test. And Mr. Brignano back there and myself, when did we do that? About a week and a half ago?
May 6th.
May 6th, we actually did a load test on that one rod. Next slide. Okay, keep going forward. There's a slide. Okay, here we go. I want to go to this one. This is, what we did is we went out on May 6th, and American Bridge and Mr. Sturgeon helped us, an iron worker working for American Bridge floor. What we did is we put, and this is a chart that shares load. How much load did we put on the rod? So we put a jack, and that's what this is. We put a hydraulic jack on the top of the rod, and we pulled on it. We pulled on that rod, and we measured how much it elongated and displaced. Okay, so some of that elongation is slip. Some of that elongation or some of that displacement is elongation. So displacement can be a combination of 2 things. Elongation, stretching of the material, as well as slip. That's rigid body movement of the whole thing. And we recognize that. and it's plotted, and it's called out as displacement, recognizing it could be two of those things. Now what we did is we didn't just test the rod in question that we saw that was short. What we did is first we identified two rods nearby, and we did a base check. We created a standard, or a basis on this is what should be. And these are supposed to be stressed up or pre-tensioned. That is, when you lock in the nut, it should be stressed up to something like 0.48, approximately 0.48. Look at that, looks really good on the liftoff. And then what we did is we did a proof test. We did a proof test up to the seismic level. We lifted it up and we pulled on it. And it gave us this kind of load, the ordinate, or the vertical axis, we call the vertical axis in engineering, we call it an ordinate. The ordinate of the load is about where we thought it should be. It picked up a stiffness. It carried large seismic levels. We actually went to the peak 1,500-year motions of the 6 time histories that we use. So we got 2 rod tests, and we feel really good about those. That's the basis. Now let's go into the rod of question, that one rod that looked funny, that gave us results that was different. Okay, that's what's plotted here, and Mr. Brignano and others generated this. And what they did is they identified that when you first start to pick up that load, it wasn't up here at 0.48. It was way down here at something like 0.15. And again, this is exactly why we wanted to go out and do this load test. We thought it looked funny. Okay? So what we were doing is explaining why it looked funny. Right off the bat, we knew there was something wrong with this one rod. Right? So the load, the ordinate, the load, it was not carrying what it should have been. And notice how this slope is what engineers and mathematicians call rise over the run. This is the rise, and this is the run. Notice how this is very, it's sloped at kind of a low angle, and this is sloped at a higher angle. So this characterizes stiffness. So it's well connected into the steel. This, it's a lower level, so it's not pre-tension very high, and the slope, how much stiffness it carries, tells us there's 2 things here that don't make sense. Okay? So with this information, and this is our documentation, there's something wrong with this rod. So this is why immediately Bill Casey and I went to Dan McElhaney, the new basically replacement for District 4 Chief Deputy and the Toll Bridge Program Manager. We asked him, can we please take this rod? And we asked the POC, and the POC agreed that we could have funding to do that, and we turned to ABF, and ABF has done a great job, and they got it out yesterday. So this is why we took it. We knew something was funny, and we asked, could we take it, and that's why we have it. Now, can we go back? In the wrong order. Let's go back. Okay, yeah, okay. So now this one rod, out of all the 422 we're looking at, something looks funny. Then we do a more sophisticated test, right? We start out being economical. We don't want to waste taxpayers' money. We start with a simple test using UT technology. Then we do a more sophisticated test to explore that one. Next slide, please. And then yesterday, Caltrans Construction, Metz, and American Bridge Floor, and Mr. Sturgeon were capable of pulling this rod out. This photograph is literally from yesterday. It is the rod coming right out. It is actually this rod right here, and everybody's welcome to come up and take a look at it. I do want to highlight 2 things here, and I'll use my voice. Usually my wife tells me I'm too loud. 2 things you can see, okay? We can see various layers of the threads up high. We can see the collar here. We can see some grout or concrete here, and we're going to be doing chemical tests on this material to find out if it is the flowable concrete or if it's the grout. But we see, you can come over here later on and take close-up pictures. The threads are absolutely stripped. Then you also see a fracture surface, and it's a pretty complex fracture surface. This is why we're going to be sending this, we're going to be preparing it appropriately. Metz knows how to do this. They'll prepare it, and they'll send it off to a laboratory where they can do the proper kind of fracture analysis that they need to do. Sometimes it's called a root failure analysis. That is, let's get to the root of why it failed. Okay? So, but we definitely see stripping of the threads, and we see a fracture surface. So it's really valuable to see that. Next slide, please. Okay, I want to take you inside. I wish I could take all of you inside the tower, but I'm going to use photographs to do this. This is a picture of Mr. Sturgeon as well as Caltrans Construction. Metz was involved too, of the process of loading all these other rods. Okay, this is Sammy, Caltrans construction engineer, monitoring. This is Mr. Sturgeon, who was operating the equipment, and an assistant iron worker. This is the system. That is the compressor, and that's what this system is right here. When you want to know about the vertical axis, how much load are you pulling on that jack? This is the dial gauge. This is the gauge that engineers monitor. So people like Bob or Bill or Sammy or Mr. Sturgeon, they were monitoring this to know how much load the jack was putting on the rods. Okay? Here's the jack right here. It's a specialty jack just for these rods, and that's what those three parts are. The three parts all come together. Okay? It's hydraulically operated. This is a hydraulic line. That's a hydraulic pump right there. Okay? And later on, Bill or Bob can explain exactly the operation of that. I don't think we can actually load the thing up here in place, but any questions you have about those things? We got the load, the vertical axis, the ordinate. The load we knew exactly from the compression, the hydraulic pressure, and we knew about the displacement when we wanted to know about it, because Mr. Brignano would put a dial gauge on there whenever we needed to do that. Okay, next slide, please. Okay, we're also carefully going through the history of these rods. This is a schedule. It's a draft. It's not done yet, but this is a draft schedule that one of our schedulers are putting together on these rods from the very beginning. There is no stone being left unturned. We're going to understand exactly every element, every step of the way, what happened with these rods. It's going to be a thorough investigation. Next slide, please. Okay, we've already talked about this. Okay, summary, couple of things here, and you're going to have to forgive me. I'm going to tweak this a little bit. Here's the summary. As of today, I asked the POC, after that one rod was soft in the plot that you saw, that I showed before, I immediately asked my boss and the TVPOC, I think it's appropriate now to go and pull on every single one of these rods with this. And I don't want to just see if the rod is pre-tensioned. I want to do an earthquake proof test. I want to load these rods up, not to just the nut being tightened. I want to verify that the worst of the 6-time histories that our structural analysis guide us in making decisions and design on this bridge, the worst of the 6-time histories, which is far and above beyond what is standard up and down the state of California, let's take every single one of those rods that we can, let's load them up and do an earthquake proof test. And that's essentially what we've done. We're now over 400 rods. I believe Bill and Bob are going to be done maybe tomorrow, maybe this afternoon, depending on how fast we get out of here. Worst case tomorrow. Worst case we'll be done this week. Hopefully tomorrow we'll be done with it. But we'll basically proof test it, seismic proof test on every single one of these rods, except for a few that we can't quite get to just because of geometry. But overwhelmingly, we've got about, Bob, I think we've got, what, 12 more to do? Or 6?
Yeah, 12 more. Yeah.
12 more, so we should be able to comfortably get done tomorrow if everything goes well. So we expect the proof testing to be done, but as an engineer, by the time you get 400, more than 400 out of 420, we're in really good shape. So this is really, really, really good news, and that's a snapshot of today. But that one rod, it's exactly what we thought, and that's why we did the simpler UT testing first. Also, the single rod that identified as short through the earlier ultrasonic testing, ABF and Caltrans Construction and Metz have successfully pulled it off. Here it is. You're welcome to come up and take photographs of it. They're carefully cleaning it. They're taking some samples, taking photographs. They're going to wrap it up, and we're going to get it to a proper laboratory where you can put it under a microscope, literally under a microscope, and we can study the fracture surface. We can study the materials that you see on the threads. We can also study the stripping evidence on the sides. And by the way, it's stripped on all sides. Okay, but here's a fact, and I'm big on facts. You can absolutely see stripped threads and a fracture surface can be seen. Also want to let you know, water samples are currently being taken for chemical analysis. Just under 100 samples are taken. I think it's like James 87. 87. Oh my gosh. James reports that we're at 87. Again, just under 100, which I feel pretty good about. And basically, we're taking as many samples as we can. If there's no water down the hole, I can't take a sample. Right? So what we're doing is we're taking samples where we can. And where we have those 87 samples, Metz and Mr. Casey have identified 25 that we think have the greatest amount of water in them, and we're prioritizing those first. So we're going after what we thought might be the most critical, and those will probably be back in a couple of weeks. We expect all the others, so the 87, to be done by the end of June. Okay, so by the end of the fiscal year, and the idea is, I would like to take the chemistry from that water and bring it back into design where I live, and I'll work with Ade Akinsanya and T.Y. Lindmoff and Nickel and the POC, and we'll take the data from the chemistry of the water and we'll update the design models, and we'll take whatever action we need to. Okay, and I guess that's it. If there's any question, I would encourage you to come up here and take a look at this. And I guess, Bill, can you or Bob walk these folks through the process? Because I think the load is huge, and if somebody can come up here and walk them through this, I think that's appropriate. Yes, sir.
Brian, just a few questions. First
Yeah.
one is,
The podium, please. Thank
when
you.
you tested, when you first got your red line on this thing, it was pretty clear to you that something wasn't straight, something wasn't going right.
That's correct, sir.
Now, having done that test and finding out that something wasn't right, and having done these 400 other tests, first of all, is this replaceable?
It's not easy to replace. I do believe we could remove these, and we could, I believe we could clean out the hole, and I believe we could actually put down a new rod, a different kind of rod, something with an anchor at the bottom, put in very high strength grout, let the grout come up to strength, and then have threads on the top, and we could pull on it, and I believe we could effectively get the same kind of structural performance out of another system. And it's very, very similar, Mr. Bakar, to what we call a tieback wall. Like when I was a young engineer working in construction over on Highway 4 by Appian, we actually did a lot of tieback walls. So we basically have a wall of 50 feet of soil, and what we do is we put pieces of steel deep into the earth, 100 feet, and then we drill a hole, put a steel rod with an anchor down at the end, and then we pump in high-strength grout. Then we let that grout come up to strength, and then we pull on it and tighten it down. I can imagine how we could do that pretty straightforward in that fashion, but I also, unfortunately, we've had to retrofit bridges up and down the state of California as part of the seismic retrofit program. The trick to when the base of a column isn't exactly what you want, one thing that you can do is come up with alternate load paths. So I can imagine half a dozen different ways to recreate a load path if these are compromised. But I'm not convinced they're compromised yet. And this is really important. Every bridge that I know that's out in water has to deal with water. It has to deal with water. Like, for example, Richmond-San Rafael Bridge. It's older than I am. Richmond-San Rafael Bridge is older than I am. All the piles underneath Richmond-San Rafael, did you know they're steel? And the water is rushing through there. The water is very, very fast. And it also carries little sand particles. So it's pitting all the time. So the steel piles under Richmond-San Rafael, we just invested as a community about $1 billion into its retrofit, and that's steel piles. The Skyway, the Skyway, all of the east spans, they are steel piles in open salt water. And we do anticipate a loss of section, but it's not a large enough loss of section that it's going to be a compromise for 150 years. Benicia, same way. So many, many bridges are out in the environment, they're out in salt water, and this is something that we're going to have to evaluate, but we've had to do this before on other bridges. I think we know exactly how to do it. We'll use specialists from Metz, but I feel like, first of all, it's too early to make any judgments. Let's do the proper engineering, let's do the proper science first, let's stay calm, let's evaluate it, and then once we evaluate it, we'll consider what do we need to do. Maybe everything is just fine. Maybe it's not, and we'll make a decision on that new information, and we'll go forward with it.
Of the 576 rods and dowels, it appears as
You mean
though-
424?
Well, 424 and 152 you said of the dowels,
Oh, yeah, yes.
which are also a seismic feature. Of the 576 of these things, does the loss of one constitute any grave or serious defect in this bridge?
No, it doesn't. You're speaking like an engineer. 1 out of 400, right? It's less than 1%. Engineers, we're the practical people of, if you will, the mathematical, scientific world. And that's exactly the kind of thing that we do. Engineering, it's never to 5%. You know, I like to say if an engineer tells me they know anything to 10%, I think they're either lying to me or they don't know what they're talking about. Things are not to within 10%, and you raise a very, very good point. 1 or 2 or 3 or 5 rods out of 400, really, quite frankly, it's not a concern. But I need to address it because we're talking about 150 years, and I can't just take a snapshot today. I have to think about 150 years in the future. Really good point, though.
Indulge me in one more question, and that is this. The bottom of those rods, at their deepest point, where the nuts are that you bolted them into, is that below the water line or is that above the water line?
It's absolutely below the water line.
So it is possible through some defect or some series of problems that salt water, bay water, could have found its way into this area.
Oh, absolutely. There are many facts about concrete. This is my experience. Concrete is gray and concrete cracks. In fact, concrete cracks by its very fundamental design. A junior in engineering school learns about concrete cracks, and the reinforcing steel inside the concrete carries the tension. Concrete only carries compression. So I can absolutely imagine tiny, tiny cracks open and some water can get in there. But the question is there an exchange of water with fresh oxygen? And compare that to the water rushing underneath Benicia or any other bridge in the world, right? There's salt water at the mouth of any river. We don't really have a fresh exchange of oxygen, and that's really a good thing. But I can absolutely imagine some amount of water getting through cracks. The question is there a rich exchange of oxygen? I don't think so. But that's something we have to go through the proper engineering. Good, really good questions.
Can you talk about the 87 water samples that were taken and where those samples were taken? Were they from, are you saying those 87 sleeves with water found inside, or where exactly were the samples from?
Out of all the sleeves, these rods, they go down a steel pipe right in the middle of it. And we asked American Bridge Floor to explore and show or demonstrate, prove to us that you actually grouted these things up. And as part of that process, they used water jetting to cut a hole to show us. In some places we found grout was there, in some places we found grout wasn't there. In most cases we found grout was there, but we did find some places where grout wasn't there. And then what we did is we're in the process right now with METS. They're monitoring the level of water. In some locations, there is water there and it's coming in. So what we do is we sample down at the bottom and we're really careful. METS first measures how deep the water is, then they get a sample of that, and when they extract it out, then they measure again how deep it is, and then construction in METS is constantly continuing to monitor how deep the water is. That gives us a sense of the flow, and I believe in the next few months, I'm going to be asking Mr. Casey, again the resident engineer, to use a contractor to either put oil or grease down the hole, or concrete grout, or grout down the hole. And what that will do is, concrete weighs about 150 pounds a cubic foot, something like 145 pounds a cubic foot. Water weighs about just over 60 pounds a cubic foot. So when he fills, heavy oil or grease or heavy grout, what he'll do is he'll create a head, and he'll basically push the water out, right? So it's hydraulics, there's an engineering theory to it, and what that will do is it will keep water from flowing, and as soon as you don't have flow anymore, then you don't have an exchange or fresh energizing of oxygen. And that's really good because you can exhaust oxygen. And once you lose oxygen, you're going to stop the oxidation process or the corrosion process.
So just to clarify, did you say that they flushed water down there and that's the water they're testing? Or was it water that was already in there that they're testing, and was it from the bottom of the sleeve?
That is a really good question. It's both. Somebody who wanted to explore and do a little experiment about flow of water, they put some water down the hole, all of the holes actually. So as we're sampling them, what we're doing is we're getting a mix. That's what we're doing. And what Mr. Casey did through American Bridge Floor, what they did is they sucked out all the water, and now Now, we believe most of the water that was flushed down there as part of an experiment is now gone, or at least most of it is. And now that's why we're retesting the water, saying, let's monitor how deep the water is, and then let's monitor, does it change at all? Most of them are not, some of them are. And then when we capture how deep the water is, then we take a sample of that. So in reality, we're getting a mix, but we've done our best to try to remove the water that was put in there, and we're trying to say what's coming in. And in some locations, it's coming in. I believe we can stop that, but as a designer, I don't want to turn this into too much of a science project. You know, sometimes KISS, keep it simple, is a really good way to do it. So when we find out, you know, what that water is, I'll probably be looking at ways to take the worst of everything Bill Casey finds, and then I'll probably figure out a design approach that addresses the worst that Bill finds, and that's how we'll go forward for 150 years and be confident. That's a really good question. You obviously have done some homework.
Have those rods been in water?
Oh, absolutely, for years.
But have those rods been in and underwater for enough years to create enough damage as to not be able to save them through the process of either greasing, oiling, or concrete?
Again, a really, really good question. Stress corrosion cracking happens pretty quickly. Like for example, on the 2008 rods, which were, by the way, manufactured by a completely different company, supplied by somebody completely different material, and the testing material, the testing that we did years ago identifies the 2008 rods, the E2 rods that broke very, very quickly, literally days after stressing. That's documented very well here. These are very different than the 2006. 2006 have been under stress for years. Here, a third of them had basically broken within 2 weeks, right, in the 2008 rods on E2. On the base of the tower, these things have been stressed up for years, so it's not stress corrosion cracking, and that's what the expert external panel identified and communicated to the POC. So that means if this is coming, or if there's a threat from corrosion, it's long-term corrosion, and a chemical process takes time. Things don't happen right away. You know, if you burn something, that's a chemical reaction. That happens pretty quickly. But corrosion takes years and years and years and years and years and years in time. So if this is a corrosion issue, and we're not there yet, but if it is, the important thing is to recognize it and take measures so we stop it. And we're ready to do that. For example, these rods are stressed up anywhere from, say, 0.3 of their ultimate strength to 0.5 of their ultimate strength. Well, I could work with Mr. Casey and Dr. Nader, and we could actually detension these and reduce the stress. And that would absolutely extend the life of these rods if we needed to do that. So we have several alternatives, but Mr. Bakar, you ask a really, really good question. If this is and we're not there yet, if this is a long-term corrosion issue, these rods have not been in that environment long enough to have any significant impact due to that, and we have time to take steps if that's the issue. But it is interesting to remember, these are 424 rods that are all from the same company, right, Vulcan. They're all from the same manufacturing process. They got transported here. They've been in the same environment. And remember, in the 2008 rods at E2, 32 of them went in just days. We've had one of these go, and we're going to explore why. So it tells me that it's probably not that kind of thing. This appears to be a one-off. When you have one rod break out of all of those hundreds of rods, it says this is unusual. There's something different, because it's not, one rod sample is not representative of 400. Now the first rod, I don't know if everybody remembers, I know Mr. Vakar will remember, and some of you that have been involved in this project will remember, this is the third rod we've taken. The first rod we took a couple of years ago, it was actually stripped during the manufacturing process. The rods were stripped, and it was never fully loaded, ever, because the threads just stripped. And that's the reason we took that one for actual material testing. Okay, so we took that one to explore the properties of the 2006. The second one, I asked Mr. Casey, find me the rod that was under, you ask a really good question. It doesn't immediately stop, but it will exhaust itself once the oxygen is depleted.
This rod broke. How much of the rod, the remainder of the rod is down in the hole that you pulled out? And is it at the top of the nut? And also, how does something break and then the stripping is on the top? I mean, it doesn't make sense. I mean, unless the break caused the strip. If it stripped, it wouldn't have broken. So I'm trying to think of why you have a fracture surface below a stripped rod.
Yes, I understand. Well, first of all, you kind of have two questions, so let me ask the first one. Mr. Casey and Metz, they're going out there now, today, tomorrow, next couple of days, and they're going to try to clean out the bottom, and they're going to use borescope technology, the same kind of technology used for like knee surgery, and it has a tiny camera that has a super magnifying glass on it, and they're going to take it down that hole, and they're going to explore what's down on the other side, what the other fracture surface looks like. Is there a nut? Is there another piece on the other side? What does that look like? That will give us more clues. You ask a really good question about the mechanism. And clearly when you see two elements here, you see stripping and you see a fracture surface, that's a complex behavior. And let me tell you, last night, about 10 o'clock, we were all coming up with feasible ideas, and you can come up with many, many, many. It's premature for us to start throwing those things out, and that's why we want to send it off to Metz's laboratory. Clean off, prepare the specimen, clean it off, transport, stick it under a microscope, and have them tell us what's going on the fracture surface. The stripping is obviously pretty clear. It's the fracture surface that we need to put under a scanning electron microscope. Really good question.
Just to follow, you've seen hydrogen embrittlement failure on the other rods.
On the 2008 rods, we've seen that.
You've seen what hydrogen embrittlement failure looks like on
Yes.
high-strength steel rods.
Yes, sir.
Is that fracture surface? It looks like it's a partial fracture and then it's a tear. It's a smooth and then the tear. That's usually the failure mechanism. That's where that little lip is there, where you can see. That looks like hydrogen embrittlement based on what we've seen in photos. Do you agree?
Hydrogen embrittlement, really the indication is, do you have intergranular separation, that kind of thing. That you need to go under a scanning electron microscope, a very super powerful system. So what you can see, if you want to look at that surface, you can certainly see there are pieces on the very outside. You can also see some curved elements. Like later on, when you guys get here and you can zoom in, you can see some shapes in the section. You can see a last final tear. You can see a little cliff there. I'm not supposed to touch it because I could damage it. So I can only point to it. You see an element, a fracture that's actually a horizontal. So there are like 3 or 4 parameters or elements of this surface that you can talk about. But to be able to answer the question, you need to go do homework. We need to properly clean it, get it to a scanning electron microscope, get it in the hands of people that do this for a living. I'm a bridge engineer. Ask me about concrete, steel, timber, foundations, truckloads. I can answer this. This is not my area of expertise. And I need to refer back to the specialists in those areas. And even though we all want to say what happened here, we need to be methodical, be thorough, get it in the hands of the professionals that do this for a living. And we've got a really, really great team that does this. So we'll be getting this off. James or Bill, will we send this off today or tomorrow?
Pretty soon.
Okay, pretty soon. Okay, we'll be sending this off to the right people as soon as Metz is satisfied that it's protected as it gets transported. But then that's where we'll have the answer. So it's going to be,
But
what do you think?
You can't say for sure one way or the other.
Okay.
On
Oh, no, absolutely not.
You had said before that the only way these rods had failed in testing was because they stripped. But here you have stripping and fracture. So obviously something that's not tension, that has to be tension relation has to cause the fracture. It can't fracture like that and it's not under tension.
Oh, this rod was absolutely in tension. Mr. Casey, Mr. Whipple back there, Mr. Brignano, a couple other people, about 10 of us sitting around a room. We built a large table. Steve, when was it, like 3 days ago? I don't know, last week, whatever. We came up with, what do you think, like 8 different potential mechanisms. So we're being open-minded. We're not saying this is what happened. We've got about 8 different potential scenarios. We're open-minded about what may or may not have caused this. And we need to let the professionals use the technology that's available, scanning electron microscopes. to take a look at what the surface looks like. And usually, like if you see cupping, then you know it's a ductile. If you see intergranular stuff, then it kind of guides you a little more toward things like stress corrosion cracking. If you see shear elements or evidence of, for example, say the bottom of this, you think of a rod, you think of a bolt, right? Imagine a bunch of steel plates in here, and you tighten this, and what it does is it pulls the rod into tension. It pulls the bolt into tension, but the pieces in the middle, they're sandwiched and they go into compression, right? Well, you think of this as being in pure tension. Well, what happens? What happens if this nut, right? Imagine, okay, it's dead. Okay, good, no problem. Imagine that 15 or 25 feet of this rod, right? Now down at the bottom, where the nut is supposed to be, say that nut is not on, say that nut isn't on like this. Say that nut goes on like this. Anybody ever done anything around your apartment or your house or your car, and you put the nut on and you foul the threads? And what happens is when you force the nut to tighten, what happens is you either get stripping or you get a combination of tension. You still pull it, but what it does is it starts to bend the rod. So you don't get pure tension. You get tension plus some bending, And that means P over A, the tension stress, plus some eccentric bending. So one side gets strained much higher than the average. And I gotta tell you, that's one of the things that Mr. Whipple and Mr. Casey and I have been throwing out. And there are elements here that kind of suggest that we need to be open-minded and not come in too quick. So we've got lots of different ideas, and they're all, quite frankly, premature. They're all feasible. Most of them are feasible. We even include a few that are not feasible. But right now, it's premature to start throwing out ideas, and we need to let Mets do the engineering that they do. And I believe we'll get that information back within weeks. But engineering and science, it takes time. If you want to guess, go talk to a psychic. But we're engineers, and that just takes time.
Any other questions?
Okay, Mr. Casey is here, Steve's here, Bob's here, Metz is here. Any questions about the water sampling? Our Metz folks are here. You're welcome to come in here and take pictures. Leah can make the slides available if you want the slides. And Bob Rignano and Bill Casey are here to talk about how we load these things and the jacks and the hydraulics.
Let me see. Please do not touch the rod. Look at it, photograph it, but just don't touch it. And Bob will give you orientation of the jacks you want.
No, that's okay. Would you do me a favor, that lady in the purple?
Yeah.
Could you just ask, just work with her? Okay, no problem.
Ask for
No, Leah, this lady, she wants to,
Okay, I'll be right back.
What we need to do is look at it. We got what now? There's so much tree down there, they're gonna put it out. But I mean, you measure all the pieces together. They're pretty close to the length.
Thank you so much.